China just announced quantum advantage. Again. The number is large, the processor is real, and the team behind it has done this before. But in quantum computing, we announced it and we proved it are not the same sentence. The entire history of this field lives in that gap. And that gap is exactly where you need to be paying attention right now. Before you decide this is either a genuine breakthrough or a propaganda exercise, stay with the evidence for a moment. Because the honest answer is that neither extreme is what the record currently supports. How you read this claim shapes how you read the entire race. It determines who you think is actually ahead, what advantage means in practice, and whether the scoreboard anyone is using reflects reality. By the time we work through this, you will understand exactly what quantum advantage means and what it does not mean, why every major claim in this field, including Google's, has been seriously contested, and what specific standard of proof would actually settle any of this. Here's the first reframe, and it matters. This is not really a story about one Chinese processor. It is about who gets to define what winning looks like in quantum computing, and whether that definition has any teeth at all. The team that produced this latest claim has a track record of peer-reviewed publications across multiple generations of hardware. So what actually happened to those earlier claims when outside researchers engaged with the data? And separately, if Google's Sycamore result went through peer review and still faced serious challenges, what does that tell us about the bar any new claim has to clear? And underneath all of this sits one more question. This result operates on physical qubits, not logical ones. Why does that distinction matter, and what does it mean for whether any of this translates to something you can actually use? Let's build the foundation, because everything else depends on one concept. Quantum advantage is not an absolute fact, it is a snapshot comparison. A quantum processor completes a specific task faster than any known classical computer could at that moment. 3 words carry enormous weight there. Any known classical computer. That phrase means the best algorithm anyone has managed to write so far, running on the best classical hardware available. It does not mean a theoretically optimal classical solution, it means the current best effort. And the current best effort keeps improving. The task itself is also carefully chosen. In these demonstrations, including Google's and Zuchongzhi's, the task belongs to a class called random circuit sampling. It is not a general-purpose computation. It is not solving drug interactions or optimizing logistics. It is a problem specifically constructed to be hard for classical computers and tractable for quantum ones. That is not a criticism, it is how science works at the frontier. But it means the advantage is narrow, targeted, and contingent on the classical side not getting significantly better. Imagine you claim to be the fastest runner in town, but fastest is measured only against the people who showed up to race that day. If a faster runner arrives next month and runs the same course, your record is still in the book, but your advantage is gone. Quantum advantage works exactly this way. The classical side keeps training. Sometimes it catches up. So the date of the classical comparison matters as much as the quantum result itself. And any claim that does not specify the classical baseline is not quite telling you the whole story. Google ran the most famous race in this field in 2019. Their Sycamore processor with 53 qubits completed a random circuit sampling task in roughly 200 seconds. Google's paper, published in the journal Nature and peer-reviewed, stated that the best classical supercomputer would need approximately 10,000 years to do the same thing. That number, 10,000 years, was Google's figure from their analysis. IBM immediately and publicly disputed it. IBM's counterclaim was that their Summit supercomputer could complete the task in roughly 2.5 days given the right approach. That was IBM's stated estimate, not an independently arbitrated number. Then, in the years that followed, research groups working on classical simulation algorithms further compressed the classical time estimate. The advantage gap narrowed substantially from where Google had originally placed it. The peer-reviewed paper did not end the debate. It opened it. Think of it like a speed record set on a specific track, in specific conditions, against specific competition. The peer-reviewed paper is the official timing slip. But if someone later finds a legal shortcut that was always available, or develops better technique, the record stays in the book, and the meaning of it quietly changes. Google's advantage was real at the time of measurement on that task against that classical baseline. What eroded was not the measurement itself. What eroded was the size of the gap. And that is the pattern the entire field has been running on ever since. Now bring that lens to Zuchongzhi. The team at the University of Science and Technology of China has produced multiple generations of superconducting quantum processors under the Zuchongzhi name. Prior generations, including the 2.0 and 2.1 versions, produced peer-reviewed publications in high-impact journals. The exact venue and generation mapping of each paper should be confirmed against the primary record rather than taken on summary, but the existence of peer-reviewed prior work is established. Those earlier claims were also subjected to classical simulation challenges after publication. Researchers demonstrated that classical algorithms could partially close the gap on the specific sampling tasks those versions used. The advantage was real as measured. The gap was narrower than initially stated once the classical side responded. The latest Zuchongzhi result is a new advantage-style claim from the most recent generation of the hardware. Here's what the record shows. The hardware is real, the team has peer-reviewed prior work, and the generational improvement curve is documented across multiple iterations. Here's what the record does not yet show, at least as of this script: whether the latest specific result has been submitted to or accepted by a peer-reviewed journal, and whether any independent research group has attempted or confirmed replication of it. That status is publicly unconfirmed. The claim exists as an institutional announcement. A track record of peer-reviewed publications is not nothing. It is the reason this claim deserves serious engagement rather than dismissal. But it is not a substitute for peer review of this specific result. Every generation has to clear the bar again because every generation is making a new claim on new hardware against a new classical baseline. The prior work earns the claim a serious hearing. It does not earn it a verdict. Here's why the distinction between physical qubits and logical qubits matters more than any number in any of these announcements. Every advantage demonstration in this field, Google's, IBM's, and China's, operates on physical qubits. Physical qubits are noisy. Errors accumulate as the computation runs, and eventually those errors overwhelm the result. You cannot run an arbitrarily long, arbitrarily complex computation on them. Logical qubits, built from large groups of physical qubits working together with active error correction, are what you need to run the computations that would actually matter at scale. Breaking encryption, simulating molecular interactions for drug discovery, optimizing systems too complex for any classical approach. The overhead to build one logical qubit from physical qubits is large. Depending on the error rate and the correction code being used, you are looking at roughly hundreds to thousands of physical qubits per single logical qubit, though the specific ratio for superconducting systems at current error rates is an active research question without a settled public number. No superconducting system has demonstrated fault-tolerant logical qubit computation at useful scale as of the current state of the field. So what does a physical qubit advantage demonstration actually prove? Think of it like demonstrating you can balance on one wheel of a bicycle for 30 seconds. That is a real skill. Harder than it looks. Not everyone can do it. It tells you something genuine about the physics and engineering of the machine, but it is not the same as riding a bicycle across a city carrying cargo. The balancing trick is evidence of progress through the generations of development necessary to eventually reach fault tolerance. It is a capability milestone, not an arrival. And that is the honest framing for every advantage claim on the table right now from any player. Here's my honest read. The Triumphalist version says, game over, China has achieved quantum supremacy, the race is decided. That version ignores that no advantage claim in this field has survived classical simulation pressure indefinitely on its original terms. The dismissive version says, this is a press release. Ignore it. Nothing to see here. That version ignores that this program has peer-reviewed prior work, a real hardware trajectory across multiple generations, and a pattern of serious scientific engagement even where the claims were later narrowed. Both versions make the same mistake. They close the gap before it has closed. What neither version will tell you is this: we are in the gap right now. The gap between the announcement and the verified record. The field has been here before, with Google, with IBM, with earlier Zuchongzhi generations. The gap always closes in one of two directions. Either the claim survives peer review and independent replication and becomes part of the permanent record, or it gets narrowed and revised and the stated advantage shrinks. Right now, we do not know which direction this one goes, and anyone who tells you they do is making a bet, not reading evidence. The gap between claim and proof is not an administrative formality. It is the terrain where the entire credibility of quantum computing as a field gets decided, for China, for Google, for everyone. Zuchongzhi's latest result is standing at the edge of that gap. The question is whether it crosses. So here's what I genuinely want your read on, and I mean this. Leave it in the comments. Which bet would you actually back right now? Bet A holds that the track record and the hardware trajectory are enough to extend real credit before verification is in. The pattern of serious peer-reviewed work across generations means the claim is probably real, and replication will confirm it. Bet B holds that a claim is not a proof, that the field's own history, Sycamore included, says the honest move is to wait for independent replication before any of this means what the announcement says it means. Both positions have real evidence behind them. Both are defensible. I want to know which side of the evidence you think is heavier and why. Subscribe, because when this result reaches peer review and when the classical simulation researchers run their own numbers, this channel will track exactly what it means and whether the gap closes or widens. The number was large, the hardware is real. The gap is still open.